So what this video is going to talk about is some of the calculations you could do with the model of hydrogen. Again, this is a pretty limited set of problems we're going to do, but again, this is how we understand hydrogen's setup to be. So what we're going to talk about is something called the Bohr equation, I'm going to write it down for you. And again, this is only for hydrogen. So you're going to say, why are we spending so much time on hydrogen? Well, that's because it only has one electron. So here is Bohr's equation. Okay, and you might also wonder why we keep talking about Bohr. But again, he was correct with the energy levels, so we can look at that way. So energy is equal to RH. RH is called the Rydberg constant. Then Z is the nuclear charge. And again, that's the number of protons. For our discussion, it's 1. You're going to wonder why we only have, like we just put 1 there, but it's a whole saga. Then we have N, which is the energy level. So again, that goes back to this diagram here. So N is an energy level, okay? And energy levels can go from 1 to energy level 7. That's the maximum we have at this point in terms of it. So going back to the Rydberg constant, I will give this to you. It is a negative 2.18 times 10 to the negative 18th joule, okay? And you might be saying, well, why do we have it as a negative? Well, we're saying that energy is being emitted. We're always talking about the energy coming out. So that is why you will see the Rydberg constant is given as a negative value, So this is, I could calculate for every energy level, I could calculate an energy quantity, okay, for each one of these energy levels. But what we care about is when the light comes out, what is that energy of light? So what we're going to focus on is this equation here. So it's going to be the change in energy. So it's going to be negative 2.18 times 10 to the negative 18th joule. That's going to be your constant. And you do 1 over n squared, the final, where the electron finally lays, versus where it started initially squared. So this is going to be the Bohr equation that you're going to use most often, rather than calculating each individual energy level. So let me show you how you're going to do that with this next calculation, okay? So calculate the energy lost or absorbed when an electron moves from energy level 6 to energy level 1. So the first question I have is the energy going to be lost or absorbed? Okay, it's going from a higher energy state to a lower energy state. So that means the energy is going to be lost, okay? And if the energy is going to be lost, my final answer has to be a negative, okay, to say that it's being lost. Similar to system versus surroundings that we talked about with thermo. So let's do the calculation. So the change in energy is going to be equal to negative 2.18 times 10 to the negative 18 joule. And it's going to be 1 over. So where does it end? It's going to end in energy level 1. So that's going to be what you put here. So it's 1 over 1 squared minus 1 over, where does it end up? Or start, excuse me. Where does it start? Energy level 6. So I'm going to put 6 squared and do the math. Okay, so that comes out to be negative 2.12 times 10 to the negative 18th joule. Okay, so that's how much energy is given off when that electron in hydrogen goes from energy level 6 to energy level 1. Well, I could also find its wavelength. Okay, so I could find the wavelength for this energy. Okay, so wavelength is going to be equal to, we did this in a previous set of problems, Planck's constant times the speed of light over energy. So I could do that very easily. All right, so you could plug that into your calculator and you could have the wavelength as being 9.38 times 10 to the negative 8th meters. which you could convert to nanometers, is about 93.8 nanometers. So I might ask with these types of questions, is it visible or not? And you would say it's not visible. So one question I have is where did that negative go? Do I need to include it? Do I not need to include it? So on and so forth. Well, the negative is to say that the energy is being lost. Can I have a negative wavelength? No. So really, I could avoid putting that into the equation if you want to just make it a plus, or you could just keep it from the calculation altogether. Because again, what that negative is signifying, just like when we did in thermo, is the fact that energy is being lost. All right, so why don't you try the next two problems. This one is going from energy level 5 to energy level 2. Find the wavelength of light in nanometers, and then how much energy is needed to excite an electron, moving it from energy level 2 to energy level 3. So why don't you try those two, and then you can click back. I'm going to pause it and then show you the answers. All right, so other than my messy handwriting here, you should have gotten the energy as being negative 4.58 times 10 to the negative 19th joule. And then you could stick it into the equation to find it in, find the wavelength in meters, and then convert it to nanometers. So again, I'm going from a higher energy state, an excited state, to a lower state. So that means that I am releasing the energy, so that's why it is a negative number. Also note, is this in the visible range? It is, between 400 and 750. Would I know that otherwise? Well, if you think of the Balmer series, anything that ends in energy level 2 is going to be in the visible range. So those are just little bits of information that might help you to answer some questions if you kind of get stuck. And then this next part, or the second equation or problem I ask you to do, you're going from an energy level 2 to energy level 3. Now I kind of gave you a hint by the fact that it was excited. You end up with 3.03 times 10 to the negative 19th joule. And notice that it is a positive number. Okay, you don't have to write the positive, I'm just over exaggerating it. Okay, that's because you're going from a lower state to a higher state. So that means you've got to put energy in order for it to move to a higher energy state. So again, the nice thing about this equation is it kind of works through that with you, so you can kind of see what that is. All right, so the next thing I want to talk about in this video is going to be what we call the photoelectric effect. Now, in order for this to make any kind of sense to you, I kind of need you to watch the video first for you to understand what I'm getting at, and then come back to my notes here, okay? So I'm going to stop here for a moment. So this is the video that I want you to watch. Again, it used to be a simulation. It's still not a simulation that we could use. It's not converted to HTML. So this is the basic setup of the photoelectric effect. Okay, what you have over here on the left is a piece of metal, and you are shining a light onto it, and you are exciting the electrons so that they leave the metal, and they travel across, and you could then record the current that you have. So after watching the video, I kind of want to give you some further discussion of it. So I have light over here, and I do expect you to know the diagram. So I have a light source hitting a piece of metal, and the electron is being ejected, and then I have a way to kind of count or see how much current I have there. So light is impinging on what we call a clean metallic surface in a vacuum, because again, you don't want anything else. And they emit electrons, okay, provided the frequency of the light exceeds a certain value. So that is what we call a threshold, okay, threshold value. And that depends upon the metal itself. And again, if you had a way to interact, you could change what metal you have there. So what do we know about the energy of a photon of light? Well, we know that that is equal to Planck's constant times frequency. So if we have the energy of the light hitting that metal, okay, and the video kind of goes through that, there are certain places where you don't get any electrons to come out. So you can change what we call the intensity of the light. Okay, so you could change it up to 100%, which is what the video kind of showed you. Well, if you change the intensity of the light, you will get more and more electrons to come out. Okay, you could get more and more electrons to come out. But what's important about the light is going to be the frequency. There has to be a particular frequency you have to hit, and that is the threshold frequency. So once it hits that, then you're going to get electrons to come out. So once it hits that threshold, okay, you're going to get excess, you're going to exceed that threshold, you're going to get extra energy out. So where is that energy going to go? So if we have the energy of that photon is due to what we call the kinetic energy and its binding energy. So BE stands for binding energy. What keeps that electron in that atom? Okay, and that was something that, again, Einstein, being a pretty smart guy, got his Nobel Prize for this, because again, scientists couldn't figure out how this was working. So if I took the kinetic energy and just rearrange this to Planck's constant times frequency minus the binding energy. So anything that exceeds the threshold, the electron is going to move faster. Its kinetic energy is going to be sped up. So again, if you watch the video and the other video, it will kind of show you that. So once you've hit that threshold, then you're going to see those electrons coming out much, much faster, because the extra, okay, so this is the extra energy that is left over once you've hit that threshold is now going to go to speed up those electrons. So when you're doing calculations with this, this is going to be no different than what we've done before. So find the wavelength of light which will eject an electron from sodium metal if the energy needed was this. So that has to be given to you. So I'm going to pause the video and then show you the answer. So you should get a wavelength about 1.49 times 10 to the -7th, which is about 149 nanometers. So again, this is no different from other calculations we've already done. It's just more specific for the photoelectric effect.